hi everyone, welcome to our CSP seminar this week. So this week we're honored to Professor Samet Oymak, who is newly joined this board to give us a talk. Samet has done a lot of wonderful work in statistical data analysis over parameterized neural networks, and today we're going to talk about some new work on transformers. Let's welcome the speaker.
Awesome. Thanks for the introduction. No need for clap. It's fine. Anyhow, so I will talk about some of our recent work. So basically it's based on 2 papers, and more papers are coming, but let's stick with this too. So basically one paper is the initial paper is called margin maximization attention mechanism. It will appear in RIPS, and this talk will be mostly about the transformer support vector machine, which is kind of a follow-up, but it has a lot of new results that we will discuss basically. So, the talk is mostly covering the red paper. So maybe I can, time to get started, I guess. So this is in collaboration with a few colleagues. So one is Davut. So Davut was a postdoc with Laura at Michigan. So now he's at UPenn. So he's one of the collaborators. Lizzie Ying Chong is here. And Xue Chen is my students from UCR, and they're actually both here, recently moved here. And Chris is my friend or colleague from my lab mate from PhD, basically. Yeah. So perhaps I want to first start with a background on what is a transformer, in case you guys are not familiar or anybody not familiar. So transformer is essentially a neural net architecture, right? And a conventional neural net architecture is all about basically taking some features and then applying matrix multiplication and nonlinearity. That's a feed-forward neural net. Convolutional neural net is a version of that. I mean, we can do recurrence and so on, but long story short, the idea is multiply with matrix and apply nonlinearity. So transform is a type of neural net architecture which is somewhat different in the sense that it's kind of particularly tailored for sequence processing. So basically, if you think about transformer, the main revolution came in NLP domain, right? Which is a sequential domain, when we think of the language. So it treats the input as a sequence. So basically there's this tokenization. That's one distinguishing feature. And another distinguishing feature is the attention. So an attention kind of calculates similarities or dot products between different tokens in the sequence. So these are the 2 key features over a usual neural net. And here's the example. For instance, if I have a text input, this is the example sentence, then tokens can be the words. And in practice, tokens are not words, but they are half words kind of thing. In average, I guess 2 tokens makes 1 word in English, approximately speaking. And another example is we can also use this in visual inputs, because if I have an image, then I can kind of split it into patches. There's a paper called an image is worth 16 by 16 tokens or something. So then it looks like this. My tokens are like this image patches, and then I can kind of correlate them using attention mechanism. So we have been discussing attention. So it turns out basically transformers introduced in the paper called Attention is All You Need. So obviously this paper is pretty well received at this point, because later on transformer architecture led to major advances in NLP. If you ask ChatGPT what is your architecture, it would probably tell you that I'm a transformer. So the goal of this talk is kind of understanding, basic mechanics of transformers and attention mechanism through optimization theory. And throughout, just feel free to stop me, if you have any questions, because if you're not familiar with some of the jargon, it might just look confusing potentially. So we have been motivating this by attention, right? Attention is all you need, or X is why you need all this paper. You might have seen a bunch of titles like that. So after the initial paper, right? So why attention? So at a high level, I guess this is kind of important to understand, right? So the model can take a long sequence, and attention kind of at a high level allows the model to focus on the perhaps relevant subset of the sequence, so that it can either generate a new token or it can make a classification decision and so on. And another important thing is, again, the key distinguishing feature from regular neural net is tokens get to interact with each other, right? They hit each other. It's kind of matrix factorization, perhaps a little bit, rather than usual neural net, because there is kind of data is interacting with each other. So this is a kind of an example, right? Attention is kind of a fairly visualizable thing. So in a translation example, suppose like I'm translating English to French or vice versa. You can look at the attention maps between the input and output tokens to see which tokens are related to each other when like there is a generation happening. You can kind of do some credit assignment basically. This attention map is kind of helping you do that. So what is a transformer, like functionally speaking? Like it's essentially obviously a function that takes the input and outputs, that takes the input and outputs something, right? So the function looks like this. So basically you essentially first apply a self-attention layer and then followed by parallel MLPs. And there are a bunch of normalizations and residual connections. So the important thing is that basically it is a sequence to sequence map, right? It takes an input sequence, then outputs a output sequence. So basically suppose input is x1 to xt, and these lowercase xi's are the tokens, and output is y1 to yt, those are also tokens, right? And then the key thing is basically self-attention gets the tokens to interact with each other, right? And then layer norm and NLP essentially applies in parallel. Basically, each token gets processed by MLP, for instance, independently. Okay, so self-attention is kind of the main interaction at this token interaction. We can obtain a larger transformer by stacking this single transformer block. So this is a single block. If you just stack it up, then you can obtain a more modern transformer. And for instance, classification or next token generation. So basically, imagine we do this layer by layer for many layers, and at the end, I can just read up the last token to make a classification decision or generate a output sequence, basically autoregressively. For instance, in autoregressive generation, we would generate a token and then feed that token to the input and generate a new token and keep going. In case of a, let's say, generator model application, like ChatGPT kind of thing. So what I want to discuss is self-attention, which is kind of the main point of the talk here. Like we want to essentially discuss the basic properties of self-attention. So self-attention layer, again, it maps input sequence to output sequence, right? But we will simplify this quite a bit, but like for now, let's do sequence to sequence. I mean, the theory will account for sequence to sequence as well, but no point getting into that because there are a bunch of obvious extensions that once you get the main idea, the extensions become clear. So basically suppose X, so basically throughout X, the capital X will denote some input example. So I will denote it using a matrix, and this matrix is T by D, and T means essential length of the sequence, and D is the size of each token, okay? So T is the sequence length, D is the dimensionality of token, and then the basic or canonical self-attention formula is like this. So we have trainable weights KQV, okay? And what we will do is basically we will create features called key query and value features. And then there is a canonical self-attention formula. So basically create key features using from the key weights. So one important remark here is that sequence length is T, but the number of parameters is only function of D basically. Which is a good thing because it processes the sequence independent of the sequence length. So in terms of the total parameters. So we got this XK, XQ, XV, and then these are all T by D. And then we will fit, so obviously we can make these different dimensions, but I'm sticking with D just for simplicity, right? So we will feed T by D, we will output T by D. So it outputs the sequence, this guy. So this is essentially the self-attention formula, right? And this S is the softmax nonlinearity. And the idea is that basically XQ and XK is a T by T matrix. And each element of XQ, XK is essentially all possible pairwise interactions between the tokens. That's the way to interpret this, okay? And then you pass it through softmax, and softmax, we will discuss the details, but this essentially induces a probability vector of similarities. And then softmax times the value essentially creates a learnable convex combination of the input tokens to output tokens. So you generate output tokens using a learnable softmax map by blending, it's kind of a blender basically, blending the values. Or you can write this in optimization or more explicit form, right? QK transpose if you plug this in. And this is the dimensions, right? T by D hits D by T hits T by D. Any questions, just stop me. So, this is good. And this you can also handle. but we will essentially focus on a cleaner form, like, where like we're only reading like one token and like kind of a classification form. So what is the form we will discuss? Like I call this optimization formulation, but we just want to make a binary classification here. We can do some more fancy things, but I will not get into it. So the basic form we will discuss is like map a sequence to a label plus minus. And original model is like the self-attention, this original self-attention outputs this, right? So what we will output is basically, rather than the original, let's just read only the first token. Like, it's kind of permutation invariant. So the first token, last token doesn't matter unless you are using position encoding, which we are not using here. Read only the first token. We can also discuss like what position encoding would do, but that's again a different story. So with limited time, we are doing a lot of simplification here. So rather than making V a matrix D by D, let's just make it D by 1 so that we can essentially use V as classifier output to essentially make a plus minus 1 decision, okay? So then our model looks like this. So essentially we will take X and we will output V transpose X transpose softmax X K Q transpose X1, okay? So basically this softmax X K Q transpose X1 is kind of given first token X1, it is outputting a probability vector condition on X1, okay? And given this probability vector S, we are multiplying the sequence X with S to create a blending, to create a convex combination of the tokens. X transpose S can be rid of a convex combination of the token. And then we are essentially doing a classification with V. So basically take a sequence, output one token, and that output token is X transpose S, and then do a binary decision with V. So if I have a training data set Xi, Yi, obviously we want to solve empirical risk minimization, and empirical risk minimization looks like this. I just plugged in my function. So this is my function fxi, and then we will multiply yi times fxi, okay? So, one nice feature of this work, I would say, is basically we have very mild assumption on L. Basically, what is the loss function? So we will just choose any strictly decreasing smooth loss. Basically, L can be non-convex. It doesn't matter for the analysis, which is kind of a nice thing if you think about it. Because, obviously we can handle logistic loss and all the other classical loss, but we can handle any non-convex loss as long as it is decreasing. And decreasing just means the fact that like making your predictions stronger, right? Just like logistic regression, the stronger belief you have, logistic loss will drop in the correct label direction. That's what we are doing. We want to make sure that model has output a strong belief, right? Fx is large in the direction, sign direction of the label. So again, just to recap, our goal is like, what transformer learns to do when you solve empirical risk minimization, in particular using gradient descent or variations of it.
So V is not a parameter?
Oh, okay. That's a great question. So in the NeurIPS paper, actually, we can make V a parameter and like we characterize a bunch of things. In this talk, I am focusing only on KQ. I'm never touching V. I will fix V and see what's happening as a function of V.
So I may miss that point. The XI1, can it be any layer or any row? It should be the first one. Or what is the significance of the first one?
So basically, it can be anything. Oh, in fact, okay, that's a great question. Actually, I forgot to mention this. XI1 is arbitrary. Going forward, actually, I will just set Zi. So in other words, like we can just solve the problem for any Zi, right? And then you can plug whatever you want later for your problem. Yeah. So if you make it a Zi, it is called cross attention. In other words, there's a sequence X and there's a sequence Z, and we are looking at the cross attention between them. Yeah. So in this case, self-attention is not that important. We can do more generally for cross. There are scenarios where self-attention is important. Again, it's not important for this talk. So we will essentially plug Zi. Basically, our tuple will be Xi, Yi, Zi, where they are arbitrary. Okay, so what is the starting point? Starting point is that like you might be wondering this, right? In this form, like why do you need K and Q together? So there are two reasons you might need K and Q together. So first of all, you can make K and Q skinny, right? This way you get a low rank matrix, which again, we have the discussion in the paper, but I will not get into specifics too much about low rank beyond the nuclear norm aspect. But once K and Q is like full square matrix, right? it can be replaced by a W, presumably, right? We will see that you can and you cannot at the same time because K and Q has a different behavior. Okay, but let's start with only just setting W and see what happens. So then like we will ask the following question, right? We set this W, we fix V, we are not touching V, and actually touching V and W together is kind of open problem, or at least like I consider it open. We are like kind of looking into it. So when we solve this, like what kind of W we will converge to, right? And then we can essentially do this gradient descent analysis, right? So what we will do is basically we have a loss function, start running optimization, run it forever and see what happens, right? You know, we will maybe converge to somewhere. And then we can also replace gradient descent with regularization path, okay? So regularization path means that basically, imagine you have access to the solution, LW, you are able to, like this is a nonconvex problem, but imagine you can solve it, right? And you solve it subject to some L2 norm regularization, and let the regularization disappear as a proxy for gradient descent, okay? So basically this R here is a proxy for number of iterations in gradient descent.
Yeah, I'm sorry, I just want to get back to, so there's a classification data set, so you're assuming X images, Y's are like the binary true labels, but isn't Z part of X? If we're
Z can be, so Z can be a different modality, for instance, or Z can be just part of X. Like it is kind of optional. Z is whatever we want to be. So that's why I kind of allow the general form. In other words, like I will just let Z be whatever. Z is a vector. So Z corresponds to the setting where I guess the query is optional. Basically, query is not coming from X, but query is coming from some other vector, which is cross-attention. Yeah. Okay. So this is clear, right? Gradient descent is clear. Regularization path is essentially as you do gradient descent, right? The norm is increasing, right? And the more you do gradient descent, the better you will fit to the data, right? So regularization path is kind of capturing that intuition, okay? So you essentially, if you solve gradient descent forever, you are trying to minimize LW. But if you do early stopping, in the context of linear regression, gradient descent behaves like a bit like ridge regression, right? So the Frobenius constant in regularization path is kind of capturing this early stop gradient descent behavior.
Assuming you start from small weights then, right? I mean,
assuming you start from small weights, yeah. Sure. Yeah. So, but the important thing is that gradient descent is local algorithm, right? In other words, if you start in a like around local minima, this guy will go to a local solution. Whereas regularization path is telling you the global behavior. So the nice thing about this regularization path is that gradient descent theories can be more complex, but this can be surprisingly simple, and it is surprisingly simple. So we will get to that in a second. So in other words, like this one will just tell you kind of approximately what's going on, whereas gradient descent is a little bit more complex, basically. So empirical insight. So I will just like discuss like some high-level intuition and then maybe discuss contribution and then go into technical. So one insight is that basically this attention is about kind of focusing small part of high-dimensional data, right? So it is naturally about sparsity a bit, right? Because you have a long sequence and you want to retrieve, I mean, it's kind of like retrieval. You want to retrieve a subset of the good subset of the sequence that is useful for your next token generation or next decision. Another thing is like attention weights become more sparse. Initially it is less sparse, but you know, it becomes more sparse over time. Here's an example. So suppose we have a frog image and at epoch 0, attention weights look like this, or attention map. And as you iterate more and more, this is kind of average attention map of a bunch of layers, I think. So as you iterate more and more, as you see that the softmax, this is kind of the softmax output of attention. That's what I mean by attention map. It's getting sparser, right? So in fact, you have this behavior. So the number of non-zeros or non-zero fraction is decreasing, whereas the weights are increasing, right? So there is clearly a relation between, you know, larger weights versus more sparsity, kind of, right? So then our essentially TLDR is basically, you know, attention selects few most relevant token, right? This is kind of what people already kind of observe empirically, right? And another observation is as we select fewer token, norm should grow, right? And then we will essentially, in a second, we will define some notion of optimal token and some attention SVM problem, some connection to support factor meshing to kind of like regress this a bit better. Okay, to proceed, what I will do is like, in case like, you know, I just want to provide some intuition based on softmax because like this support vector machine connection comes from softmax. Okay. So if you're not familiar with softmax, it is good to go over so that like it's very clear. So softmax again takes the input vector v and outputs a probability vector, right? So it takes input and outputs to simplex basically. And this is kind of the softmax formula. And it's softmax at a high level, like if you are familiar with logistic regression, it is just generalization of logistic regression to multinomial setting or multi-class classification. So and the cool thing about attention is that basically while softmax is like typically what you do for multi-class classification, you are doing it here within the sequence, right? So some properties of softmax is it is a probability vector. And second property is that because of this nature, exponential tailed nature, it is always from 0 to 1, right? So it is strictly greater than 0 and strictly below 1, right? So what does this mean? If you ever want to make softmax 0, 1, right? So when the softmax is 0, 1, it's called like hard softmax or saturated softmax. If you ever want to achieve that, make softmax entries 0 or 1, you need to make softmax weights go to infinity. Because as long as the weights are finite, e to the something is positive. As a result, you cannot hit 0 or 1, right? So you have to let things go to infinity. So this is kind of the first thing, right? Second thing is what does attention do? Attention, again, going back to this, you can be in this form, right? You have X transpose S, where S is kind of the blender of the token. You are blending the tokens. And X attention is equal to X transpose S, right? So you are creating a convex combination of tokens. And this is kind of X attention here, right? And then you ask yourself the following question. Suppose somehow, for whatever reason, I want attention to select only one token, okay? In that case, how can that happen, right? Because if attention selects only, let's say, K token, then softmax should be 1 exactly at K, right? And that can only happen if W goes to infinity, right? So basically this intuition, you can build on it to kind of formalize what is going on and this SVM connection. Okay. So basically this exponential tailed nature of softmax will kind of get us that. Because what I am saying is that if attention should truly select very few tokens, right? If you want to truly make softmax equal to 0, weights have to grow to infinity, which is what we showed in the previous picture, kind of, right? Because weights are growing. So what are the contributions? So I will summarize the main contribution. We characterize optimization geometry of self-attention layer, and specifically focusing on this KQ aspect, right? In other words, like I'm letting the value weights to fixed. But again, we have some discussion on that, but that's the other paper basically. So basically what we find is that attention weights converge to a SVM solution that separates optimal token, and we will define what is optimal, because when you say optimal token, it raises suspicion, right? So, but attention goes to SVM solution that separates optimal token from non-optimal token, okay? So basically, attention converges to a support vector machine problem, but normal support vector machines separate plus from minus, right? It separates negative labels from positive labels. Whereas this guy will separate some elements of the sequence from some other elements of the sequence. Its job is not assigning label. Its job is separating the sequence into good, bad parts in some sense. So SVM bias is arising because of tendency of softmax to select optimal tokens. In other words, because in order to make softmax 0-1 behavior, that's where the SVM bias is coming from, okay? So this also explains obviously how attention induces sparsity, because at a high level through this SVM connection, what you have is that if you're on the wrong side of the SVM, you get zeroed out by softmax. If you're on the correct side of the SVM, you are capped and you get a non-zero softmax probability. So what is kind of cool about these results, at least from my point of view? So obviously there is transformer and attention, like which is kind of a reasonably near topic, and it's an important topic. And it kind of connects well to some like classical machine learning themes, right? Support vector machine around for 30 years. Sparsity, again, like conceptually people know that attention map is kind of sparse, but kind of we explain that, right? And there is even connection to nuclear norm discussion. I mean, this is kind of, again, not like fully solved problem. In fact, like there is more open problem than what we actually solve. So as SVM and token selection is already kind of connected to classical topics, right? So there is also some connection to low-rank factorization and nuclear norm. And why is that happening? That connection is happening because in the canonical self-attention, there is K and Q factors, right? And when you have this K and Q factors, and when you run gradient descent on K and Q, essentially running gradient descent on matrix factorization, it's known that basically it has bias towards nuclear norm regularization, basically, nuclear norm penalty. So there is also some loose connection over there. So this is kind of the high-level contributions, and what I want to discuss, like essentially, we will also touch more technical aspects in a second.
So SVM is a linear classifier. So are you here assuming that the tokens already like have linear separability between each other? Or
yeah, basically when the SVM applies, we are assuming tokens are linear separable.
okay, so basically you think there could be a like linear embedding of those tokens such that they become linear separable, and then
yeah, sure. We are not touching nonlinear embedding here, but yeah,
okay.
Absolutely, yeah. So there is a bit more catch because, like, first of all, the problem is non-convex, right? So you might be thinking that since the problem is non-convex, how come there is one SVM that explains everything, right? The answer is obviously no. There is actually a bunch of SVMs. So basically, from gradient descent point of view, there are many SVMs. So basically, solution goes to one of the many SVMs, and in fact, even that's kind of not fully solved problem, right? But what we know for a fact is that it can go to solution of one of the many SVMs. Secondly, we discussed like how if you have more over parameterization, there is essentially you end up with a single SVM at a high level, right? And again, some of these discussions, like some of them are conjecture, some of them are foolproof, right? So in other words, I'm just discussing. So another thing is that basically, so you might be wondering whether this kind of theory can be generalized to MLPs or future nonlinear layers. And it turns out, I mean, we have some evidence and upcoming work that, yeah, it can. So we will also discuss the evidence basically. So in fact, like this MLP nonlinearity is critical for kind of getting a rich SVM formulation. So without the MLP, if you just have this V output, you get a kind of simplistic form. With the MLP, you get a kind of richer form, and I will explain what I mean by that. And as I said, I think one exciting thing is I think there are like interesting open problems in this space. I mean, I can count 10 off the top of my head. Yeah. So I just want to start with a numerical example. So one numerical example is basically this LW, right? Just optimize W. And another numerical example, and this is what you get. Okay, I guess I was going to jump to the next thing, but so here is what it looks like. I mean, what does this discussion looks like? Okay. So suppose like we want to solve a problem with only 2 inputs, only 3 tokens, and in 2 dimensions, extremely small, right? And those inputs are shown here. We kind of zoomed out here to show what is happening geometrically, but those inputs are the stars and stuff you cannot see. The point is that gradient descent is a trajectory. So these arrows are the gradient descent, and the straight lines are the SVM directions, okay? So by solving a SVM, you can calculate some directions. You solve the SVM, get a SVM solution, it will give you some direction. And then the theory is that basically gradient descent will track the SVM direction, okay? So in other words, the gradient descent parameter is not converging to SVM parameter, but instead basically direction of gradient descent is converging to the direction of SVM, okay? So this is called like directional convergence. Again, it is well studied in the context of like this logistic regression or implicit bias of like, classification problems. But here we are discussing this token separation, okay? So why there is 2 lines here? The reason I added 2 lines here is the fact that W is 2 by 2, right? It is a 4-dimensional thing. So I cannot show you the W vector, but instead, like I'm essentially showing projections of W onto Z1, Z2 tokens. So basically I'm showing you the query embeddings here, whether the query embeddings are correct.
Can you elaborate what is the SVM setup exactly?
Oh yeah, so I will come to that in a second. I mean, maybe in a few slides. So basically there will be a clear SVM, let's say, problem. When you solve it, then you get the straight lines.
Okay.
Yeah. So before that, I wanted to just discuss that how, like, what I mean by this SVM equivalence, right? And this is the W optimization. And with W optimization, we show that the implicit bias is basically a Frobenius norm. And if you do KQ optimization, then your implicit bias of gradient descent becomes like nuclear norm, which means that you are solving SVM with nuclear norm objective rather than Frobenius. And then you can show that it similarly tracks the behavior basically. Any questions, just feel free to stop me. But this is kind of like the distinction between KQ versus W, where this is nuclear norm kind of solution. This is like Frobenius norm. I just want to discuss connection to prior work. Again, like there is a lot of prior work, but I will do some high-level summary. So there is a large literature at this point that connects basically exponential tail losses or logistic loss on separable data, and how like essentially when you train logistic loss, let's say even for simple logistic regression, forget about neural nets, right? If the data is separable, then the logistic loss essentially goes to infinity. The parameter will go to infinity, but the direction of the parameter will align with the SVM solution, which is kind of what we were discussing here, right? So basically, this direction aligns with the gradient descent direction. And as a result, basically, logistic loss connects to SVM, right? And this SVM is the traditional SVM that separates plus from minus. So then the basic observation is that softmax, softmax attention, attention has softmax in it, and softmax is exponential nature, right? Just like logistic loss or cross-centered loss. So as a result, what we are getting is that we are connecting formally attention to attention SVM, and attention SVM, the cool thing is that it is different than the regular SVM. So what are some key differences from prior work? So basically, we are able to analyze basically composition of non-convex loss plus nonlinear softmax that applies on the input. The problem is kind of non-trivial geometry, which we will discuss in a second, but without going into too much details. As a result, actually, you need some different proof techniques. And the other nice thing is that basically we are not solving regular SVM, right? Our SVM is kind of has a different job basically. It separates the inputs content rather than separating different inputs. Okay, so to proceed, we just want to discuss the intuition on what's happening. And the setting is this, right? This is the optimization we want to do. And suppose like loss function is decreasing. Okay, so basically my job or W's job when I optimize is minimizing this guy. But if I assume L is decreasing, then W should minimize the inner summation, right? W should minimize this guy. And this inner summation, it is Xi transpose softmax. As a result, I can write it as summation of ST. ST is the T entry of the softmax times Yi times V transpose XIT. XIT is the T token, right? So basically, I can decompose this. I can rewrite this sum. I'm not decomposing. I'm writing the exact same thing in terms of a convex combination of Yi times V transpose XITs, okay? And don't forget that basically summation of STs are equal to 1. So when you are given all this information, right? Then there is a clear thing to do to optimize this, right? Clear thing to do is kind of picking the ST to be 1 at the best location. So we will call this token score, okay? So Yi times V transpose XIT is like how useful that token is in some sense, token score. Then we can define the optimal token based on this token score or based on this notation, okay? Optimal token is basically simply just picking the token with maximum element. So why do we call this optimal token? We call this optimal token because like if you want to maximize this, you want to set this to be exactly 1 at that point. So as a result, you can have the following kind of straightforward lemma, right? The lemma says that for any W you choose, your training risk is always lower bounded by the risk evaluated at the optimal tokens, right? Number 1. And secondly, the only way to hit this is basically letting W go to infinity and selecting optimal tokens. So basically, why is this happening? Why is this lower bound? This lower bound because the best you can do here is setting S opti equal to 1 and everything else to be 0. That's the best thing you can do, right? So again, just to recap, right? Can we ever achieve this loss? This is the lower bound, right? For fixed, if I'm optimizing W, this is the lower bound. Can I ever hit this lower bound? No, but I can actually, right? If I essentially let things go to infinity and this W makes sure that S of is equal to 1, then I can achieve the lower bound, right? So that's why basically we have this directional convergence. Things are going to infinity because this W is trying to exactly select the optimal token. Like in other words, it's trying to get this 0, 1, 0, 0, 0 behavior. Any questions? Okay.
So this optimal token idea basically tries to guarantee that there's a feasible solution for when you set that opt I equal to 1 for all i's, right?
Yeah, so basically, we don't know if this is feasible, right?
Yeah.
So that it may or may not be feasible. That's a different story. But if you consider the unconstrained problem, in other words, if you let this ST to be whatever, as long as ST is from the simplex, then this is the best thing you can do. So then the question is whether there is a W that can select optimal token. Yeah, and that's why basically the problem has to be feasible to be able to do this. Yeah. So basically the theory will say that like one layer attention is biased towards a hard margin attention SVM, which separates optimal tokens from non-optimal tokens. So the form of the SVM is this. So this is the form of the SVM. So what does this SVM do? So essentially this SVM's job is basically making sure that for a given ZI, right? For this ZI, W picks opt-I rather than any other index. That's the job of the attention SVM, okay? So basically find the minimum Frobenius norm solution so that like W, so when you calculate the softmax similarities, opt-I has more similarity to ZI compared to any other token XIT. That's the interpretation. And then once we let W go to infinity, softmax will saturate and ZI will get picked up. ZI will exactly pick up opt-I. So this is the max margin solution, right? So, or like, you know, the SVM problem, and this is the margin maximizing solution. And now, you know, I'm not jumping the gradient descent right away. That's why the beauty of regularization path, right? Now define the regularization path solution, right? And again, regularization path is just a proxy, right? It's not gradient descent, but it's kind of just trying to capture the properties of it, because it will behave like kind of a ridge regression kind of behavior, okay? And then the theorem says that, you know, let regularization path go to infinity. In other words, like let relax R to get ridgeless regularized path, right? As R goes to infinity. Then regularization path will converge in direction to the max margin solution. So if you relax regularization path, right? Weights will go to infinity. I mean, I guess I forgot to write it here, but this WR will go to infinity. But even if the weights go to infinity, its direction will go to a fixed direction, which is exactly the max margin direction. Okay. Yeah, so basically weights go to infinity, direction converges. So next up, you can essentially go ahead and do apply similar idea on the KQ parameterization, okay? So basically, if I was solving attention with K factors and Q factors rather than merging them together, then because this low rank factorization has nuclear norm bias, right? You would essentially get this nuclear norm constraint form. I mean, normally there will also be some rank constraints here, but I avoided them to make the notation more simple. So long story short, as long as the matrices are D by D, we will get a nuclear norm constraint, okay? And we will exactly solve the same idea. And then, you know, the same result, right? So you have this regularization path where K and Q are L2 constraint or Frobenius constraint. Let the regularization path go to infinity, right? And regularization path will converge in direction to the set of minimum nuclear norm solutions. I mean, so basically this calligraphic W is just indicating the fact that maybe there is more than one solution, but regardless, it will just converge in direction to the set. Some element of the set, basically. Okay. So as a result, this summarizes basically for W parameterization or KQ parameterization, how regularization path behaves. Any questions so far?
So this,
go ahead.
This is for the case when you want only one token.
Yes.
One option.
No, but no, it's not. This is literally what happens when there is what. So basically, as long as, so basically, if you look at this definition, as long as this guy is unique, right? Suppose there is a unique guy that maximizes this token score. So this opt-I is the unique index, right? Which, if things are continuous, this is almost surely, right? Because, you know, if X is a continuous thing, right? Almost surely there is a unique index. And if there is non-unique, you can adjust the theory. But suppose there is unique, then what I'm saying is that regularization path will select single guy. And this is in fact a shortcoming of linear model, in the sense that if V is linear, it's kind of a shortcoming because it selects only one token, right? Which kind of feels bad, right? You have this whole sequence and you are selecting only one. This is why, like, we will also discuss the MLP aspect, and we don't have any like theory there, but we have a form which predicts kind of potentially what's happening. So yeah. Other question?
Oh, is it? So which is preferable, the W or the KQ parameterization?
In practice, I don't know the answer. I mean, so yeah, honestly, I don't know. I mean, but I think everyone is doing KQ. One question I don't know is whether they use KQ in a skinny way. In other words, like they are using d-dimensional KQ or like they are doing low rank factors. So if you want to do low rank factor, I guess that might make sense. If you are doing square, then the question kind of boils down to perhaps like whether the nuclear norm bias has any benefit, maybe. Yeah. Okay, so far basically what we are discussing is that regularization path selects like the token opti from the sequence xi, right? It's a very simplistic behavior, and opti has a very clear definition, right? So, but like the question I want to ask is whether like this kind of shows the true behavior, and the answer is no. Okay. So basically, this is like as D increases, this is telling us basically what kind of behavior we observe in practice. Okay, by practice we mean we are solving random problem instances for increasing D dimension. And what we observe is that basically red bars, global, is convergence to opti. So this red bar is the scenarios. The problem is indeed converging to opti in the SVM direction. Blue local bar is converging to some SVM solution, but it is not opti, but it is alpha I. Okay, so it's some other indices it's converging. So there is dependence on initialization. Okay, and the other thing we observe is that larger D, initially you don't get this SVM convergence, you get this other bar, right? But then you start getting full blue bar, and then you start getting full red bar. So basically, there is a couple of interesting behavior here. So for instance, why this can happen, right? If D is very small, again, why? Because problem might not be feasible. And if problem is not feasible, then how can it select the optimal token, right? Because there is maybe too much data and very small degrees of freedom. Optimal problem is not feasible. So in short, like what I want to discuss a little bit is basically what is our findings on gradient descent theory. So long story short, like I guess the first finding is that there is certain alphas rather than the tokens opti. There is some alpha configurations, like some other alpha I tokens. Gradient descent can prove to select them. In other words, like if you initialize it well, it will converge to a solution which selects alpha I rather than opti. So the definition is, so basically we can define what is a rather than optimal direction, which was a clean definition. We can define locally optimal direction in terms of geometry. It's a very geometric definition. If you have time to understand it, it will eventually make sense, but not right now. I mean, we can do it. I mean, it's a different story, and like I think looking at the paper is just more informative, basically. But what does it look pictorially? Pictorially, it looks like this. At a high level, what we are saying is that the optimization space you can partition into cones. Like I'm loosely speaking here, not fully rigorous, but you can partition it into cones so that there is a blue cone, there is a red cone, yada yada. And maybe this red cone is the scenario where if you initialize here, you will go to the optimal solution, globally optimal. Whereas blue cone, if you initialize here, you will go to the solution of this some other alpha which is not optimal. Okay? But you can only converge to the solutions where alpha satisfies this weird definition. At a high level, that's kind of, yeah. So basically we introduced this definition, right? So this definition tells you which kind of alphas you can potentially go. Yeah. So this essentially captures the non-convexity of the problem, right? So well, what kind of theoretical result we have? What we have is that take this gradient descent algorithm, right? And try to understand what it does. And long story short, the first result is that for locally optimal alpha, in other words, if alpha obeys the locally optimal definition, and if you initialize alpha in this blue cone, let's say, right, then gradient descent will converge to solution of the SVM with alpha, solution of the local SVM.
So can you elaborate more on the local SVM to the previous SVM?
It is the same. it is exactly the same. Usually, it is just that basically rather than, let's say, optimal tokens, whatever their indices are, you are solving the same SVM to separate some other tokens alpha. Basically, rather than selecting the optimal tokens, this SVM selects tokens alpha I. But the theory says that basically you can only converge to locally optimal tokens. So basically, regularization path was always converging to a strict definition of optimal, right? But now there is this definition of locally optimal. Okay, and if alpha satisfies that local optimality definition, which is a more general definition than global optimal, then you can also converge to those alphas. And alphas are just indices. In other words, alpha is, let's say, alpha 1 is maybe 2, alpha 2 is equal to 5, some indices from 1 to t. Is it clear or? So the idea is generalizing the original thing, where there was a single index opt I, and we could only choose that guy, right? Now basically, you can choose other indices. There is essentially a bunch of indices, as long as they satisfy this local optimal definition. Yeah.
Are you able to find the relation between the number of alphas that you can converge and maybe the cone region, like the area of the cone region that you can converge to that alpha? Is there?
I mean, we don't have much. I mean, I can tell you what we have. I mean, we didn't try to calculate the number of alphas or size of the cone. Size of the cone has a basic connection to SVM margin. I mean, basically, if this SVM is very feasible, then the cone is larger. So I have some slides for that, but I kind of removed that. But maybe I can discuss at the end, depending on if we have time. So there are some connections, though. I mean, there is some interesting stuff. But we didn't try to count it. But we have some. But I will get to that in a second. Yeah. I mean, so we can then ask basically, we are converging alpha right now. Can we converge to global optimum? Let's try to go to opt I, right? And so basically, I want to understand this picture. So because what we are saying is that look, as D increases, then initially you get all blue, which is only local convergence. I mean, basically it always directionally converges. And then you also get red later on. So what is the theory that what kind of global theory we have? Because initial theory is local, right? So we want to understand a little bit global theory. And to be honest, there are a bunch of open problems here. In other words, we by no means solve the problem, right? But on the other hand, describing the conjecture is a little bit out of the content of the talk. So number one, if all tokens, basically you solve this global SVM problem, right? And suppose miraculously, okay, you solve this problem, and suppose after you solve the problem, you realize that all the SVM margins are tight, okay? So they are all equality after you solve it. So in the high dimensional statistics, this is called there is literature on this proliferation of support vector meshes, okay? So if the problem is very high dimensional, everybody becomes support vector. Because originally you have very few support vectors in low dimension. But high dimension, everybody can become support vector. If that happens, right, if for this problem everybody is support vector, then we know for a fact that there is no stationary point and gradient descent converges to infinity, which explains the blue line. Okay, so basically, as D increases, this proliferation will happen and blue will pop up. At a high, I mean, I'm loosely speaking, not fully rigorous, but just intuitions. Secondly, imagine the scenario this, right? Suppose not only this, right? Not only basically this SVM, everybody's support token, but suppose for all SVMs, everybody's support token. Okay, this is very even stronger criteria. In that case, then there is the globally optimal solution is the only solution that obeys the locally optimal definition. Okay. Then essentially, intuitively, it explains why the red bar is happening. Because the claim is that once everyone is support vector of each other, by our definition of locally optimal, there is no more locally optimal left. There is only one locally optimal direction, which is globally optimal, and that's the red bar. But we don't have, I mean, this is the intuition, but we don't have formal proof. So we have a conjecture and stuff basically in the paper. So this is essentially kind of the geometric behavior in the sense that as D increases, we connect the increasing D to the proliferation of the support vectors, which means everybody's support vector of each other when we solve the problem. By all token support vector, again, I mean that there is no strict equality when you solve it. It is all equality, basically. There is no strict inequality. Another thing is that we have some other results. I will not get into that, but these are actually also pretty interesting, but in the interest of time. So under certain regularity conditions, so you can view this as regularity conditions. So for instance, we define the scores, right? If the non-optimal tokens have approximately equal scores, then you get global convergence automatically. Basically, you get global convergence from anywhere you start. So this condition means that basically optimal token is very clear, and all other tokens are approximately same behavior with respect to optimal token. They are not very strong or distinct. Because once you have distinct tokens, you get this locally optimal behavior that means that you might converge the local direction. But if they are all non-distinct, then there is guaranteed global convergence. And also another condition is obviously if initial gradient is favorable, this gradient can land you in a cone of convergence from which you can converge. Okay, so this is kind of the last few slides I want to discuss. So, and this is kind of not, so I'm saying theory, but we don't have full theory for this, but I will describe what we have. So far we have been discussing basically just like V, right? Basically we have this V, which is a linear model, right, at the end. What if we kind of make it non-linear, right? So in this case, what we have been discussing is, let's say, regularization path or gradient descent, attention selects one token. So, but like, what if we look at this scenario, okay? So there is a nonlinear head H, and now what will happen? So, like in other words, this SVM discussion is restricted to this like clean setting, linear setting, or like it can account for nonlinearities. Okay. So first of all, like I will not get into details, but like we have like lemmas and theorems and so on that says that if H is, let's say, convex or concave, but it's not linear, right? Then therefore certain H, we can, as you modify the H to be more convex, for instance, or more concave, then the problem probably selects more and more tokens. In other words, the optimal solution, even with the regularization path, tends to select multiple tokens and compose them. So this is not hard to see, but I'm avoiding this discussion at least in the interest of time. So as a result, basically nonlinearity is key to selecting multiple tokens, right? And then the next question becomes, look, like this formulation is only trying to select alpha I from the whole sequence. It's selecting a single alpha I coordinate from 1 to t. Then the natural question is, how should we adapt this, right? So that basically it can, there's a more general SVM form that helps select multiple tokens. So this is essentially what I will discuss. In other words, like some, yeah.
The H is fixed, or
Sorry?
H.
H is again fixed here. Yeah.
So what's the typical choice of H?
So H is a nonlinear neural net.
Oh, okay, so
Yeah.
in practice, like training variables. In training, in practice, it need to be trained.
H has to be trained. Yeah. But here I am fixing, basically just trying to understand what happens to the inner SVM thing. Okay. So because the interesting thing at this right now is basically, as long as H is linear, it's kind of degenerate, right? It's degenerating into selecting one token. For any fixed V choice you have, it selects one token, which is kind of not very favorable, right? Because like you have a whole sequence, why would you select only one? Like, but the discussion we want to make now is that if H is nonlinear, right? Again, it's fixed just like V to the generalization. Then like, can you select multiple? And the answer is yes. And the question is then, so basically imagine the following general question. Forget about this setting where H is fixed or not. I'm asking you the following question. You solved the whole transformer, it converged to somewhere, right? You trained H, you trained every single layer, right? And if you run it forever, right? In other words, you look at this eventual implicit bias or something, right? What is the general form of the W? Even if you train a multilayer transformer. Okay, so that's kind of what we want to understand. So the general form, right? Even if you do a multilayer train everything all together, right? So let's imagine the following. Suppose we run the gradient descent and we look at the softmax output, and softmax output are non-zero. In other words, they are selected over some indices OI. Okay, and this OI is a subset of T for each input. This is a reasonable assumption, right? Some softmax will be zero and some softmax will be non-zero, and OI is those softmax elements who are non-zero. So these are essentially the selected guys or optimal guys, but now there are multiple of them. And the claim is that basically W gradient descent solution, as time goes longer and longer, will be a superposition of a finite correction term plus the SVM direction. Okay. So then this decomposition kind of allocates different jobs to finite correction term and SVM component. The job of WSVM is exactly what we discussed so far. WSVM's job is basically making sure that OI, the selected guy, is separated from the complement. Okay. So basically it will set everything 0 except OI. But it's just more general, right? Because now rather than a single opti, it can select the whole set. And the job of finite term is among the selected guys, you need to allocate the softmax probabilities. How do you allocate them? And this finite guy is essentially doing that. Okay. And then again, the idea will be that basically SVM solution will go to infinity, so that basically this OI is selected, and finite guy will just like allocate what is the softmax probabilities. Because suppose you are selecting 4 tokens, do you want to assign them 25% each, or do you want to assign them 10, 20, 30, 40, right? So WFIN will do that assignment basically. And what I'm saying here is pretty broad, right? I'm saying that basically you train everything, you find the W, what happens, right? So it's not about 1 layer, 2 layer, 20 layer. So then essentially you can create this generalized SVM form whose job is basically separating OI from O bar I, right? But it has to be equal on the OI. So within OI, it preserves equality, because within OI, it will be correct by WFIN. But between OI and O bar I, basically, you want to essentially suppress the O bar I. And WFIN term, we also have a form for that. So I guess the final thing I want to get is, yeah.
So for this problem, can you also model this with SVM with soft margin?
Potentially, I think that's a good idea. I mean, no, I don't know how exact it will be, but it makes sense, right? Because this hard margin is happening when things go to infinity, right? And soft margin can maybe capture finite effect. But then the question, and I don't know the answer to this, is like, for instance, for classical logistic regression SVM connection, did people do that? Because if people didn't do that for classical logistic regression SVM, then why try this? Because this is just like more messy. Yeah. So what I want to show as a final proof of concept is just saying that how, like in a toy example, like what happens, right? So in other words, we have this idea, and I'm just asking whether this idea works in experimentally. And here's what we got. So what we are showing here is basically 3 different curves. So the first curve is, so basically we let gradient descent converge somewhere, right? We solve the problem, it converges to somewhere. And then first curve is basically, our fit based on selecting only 1 token. In other words, if you just try to understand what's happening with only 1 token SVM, you achieve a correlation coefficient of, let's say, 89% or something. Okay. So in other words, like eventually, how well is the alignment? Not that well, because you achieve like 89% correlation coefficient. If you only look at the SVM component, in other words, if you only look at the solution of this and try to explain what's happening, you achieve a correlation coefficient of like 9. This is like 99, maybe 98%, right? So these are 98%. And if you account for both SVM and the finite correction term, then you achieve a correlation coefficient of 99.5%. So this is just saying that basically, indeed, we can explain basically this multi-token selection using the generalized theory, at least like, on this toy example. So, but again, we don't have any theory for this, and, like there is some work we are doing, but yeah, I mean, it's mostly open problem. It's actually fully open problem. Yeah, and this is like below, this is 99% correlation. So in summary, basically, just to wrap up the talk, so we discussed some optimization theory for attention and transformers. The key is basically, understanding attention by noticing the fact that it has softmax in it and connecting to hard margin SVM problem. I guess one important takeaway is that rather than like max margin classifier, right? So we have a max margin token selector. So that's the main distinguishing feature. of like this attention aspect. So parameterization matters, right? Because we can have Frobenius or nuclear norm bias depending on KQ versus joint parameterization. So, I mean, as I said, basically the last bit of the slide is indicating that, you know, perhaps like you can explain, you know, for any optimization problem, perhaps there is some SVM hierarchy you can discuss about, right? And I'm not saying it is as simple as just bunch of SVMs, right? As I just mentioned, there's a correction term and all those things, right? So it is something to think about though. And again, like this non-linearity is totally open direction, but I think we have evidence that, you know, the theory can be extended. And I like the fact that it's richer SVM, right? In the sense that rather than one token selecting, multiple just makes the problem more interesting and more realistic, basically. Because, you know, that's like, let's say ChatGPT is not looking at only one token from your sequence. So some future direction, again, I will not get into all of this, but there are many things like we didn't fully discuss, right? So basically, we don't have explicit convergence rates. Like there's this implicit bias issues. We didn't discuss generalization, this MLP aspect, whole bunch of things. Yeah, I mean, even this is interesting direction. Just jointly optimizing W and V. We have some results in the NeurIPS paper, but you know, but the gradient theory is kind of open. And yeah, this kind of concludes the talk. Perhaps I can take questions.
Thanks a bit for a great talk. Any questions from the audience?
I have a couple general questions, if you don't mind, about the architecture. So what's the purpose of the parallel MLPs in this architecture? I mean, that's just a special case of a wider MLP, but with constraining some of the connections to be zero or something, right? What's the intuition why that's better than?
Oh, I see.
I think it is anyway.
Oh, I guess no. I mean, I guess in general, if you just do one big MLP, probably it is better, right?
Okay.
But the question is like, I mean, again, I'm not the most empirical person to answer this, but the question is, I guess, whether do you get any benefits versus what you are sacrificing, right? Because like if the MLPs are parallel, then you can make the inference parallel.
Oh, I see. The computation after that. Okay.
Yeah.
Not a model parsimonious as well, right? There's maybe.
Maybe, yeah.
Okay. And then the other question is about, so speech or language is obviously sequential, but the patches in an image, you know, what sequence do you use?
No,
right?
there's no sequence. Yeah.
Is that right? Okay.
It's just more like then you are treating like set, right? So when I say sequence, especially if there's no position encoding,
yeah, right.
then it's just a set.
I see.
Yeah. So that's why I was mentioning you can pick the first token or last token. Yeah.
But in speech, the order matters, right?
Yeah, but even in vision, I think there is probably visual positional encoding, I suspect, because you know they have to encode the location of the patches, but there's not a sequence.
Okay. Thank you.
Yeah, I mean, again, you might ask like, what is the role of position encoding vectors and so on, and I can discuss it like a few more minutes because we have some more results that I removed. But yeah, like what is the connection to cone width and so on? Because like. So basically, when you add position encoding, like, you know, most likely you are changing the width of the cones, like kind of thing. Yeah.
Yeah, I have a question about the convergence rate. Yeah, when I recall I reading Sodry's 2018, the original implicit bias paper, they give a convergence rate for like the binary SVM bias.
Sure.
And to me, like
I mean, logistic regression convergence rate. Right?
Yeah, and I think the logistic part is like the softmax. You're like.
Sure.
My understanding is like a multi-class version of Sodry's paper in the token space.
Sandra, yeah, sure.
Sodry's.
Yeah.
And
so they do have convergence rate.
Yeah.
1 over log T or like, yeah, I guess 1 over log. What was the convergence rate? 1 over log T, right?
Similar, although it's like proof is very complicated.
Sure.
So
no, it's fine. Actually, this is something we are working on. In other words, we will have probably a paper on the convergence rate, and actually. The result is kind of in line with Saudry, yeah. But again, you know, I mean, before convergence, yeah, there is a bunch of, yeah. Convergence rate is good question. And like, my concern is it is a little bit more on the boring side because as you said, right? From Saudry, you can almost predict what the convergence rate will be, yeah. So we are kind of looking at the paper where we are joint optimizing this and trying to understand also the convergence rate. And then that conversion rate behavior becomes a bit weirder because then you get some log terms depending on the situation. Because if you are doing logistic regression followed by softmax attention, then you get double exponentials, which kind of gets a little bit more tricky. I mean, these are getting into details, but all I'm saying is that, yeah. Because if you are just only doing, let's say, just softmax attention, right? You would expect whatever salary's rate is, you would expect similar behavior because there's one exponential nature here. And if you do softmax plus logistic, then it gets a little bit tricky.
Could you elaborate about the positional encoding thing? Because I noticed that in the UNS that is used in diffusion models, they actually use attention layers, but they actually don't use positional encoding. So they directly, they don't most of the model, the UNS model doesn't even use a positional encoding, but they still can generate good images.
I mean, again, like I'm not like as like up to date with like the applied aspects. All I know is basically position encoding is probably particularly important for sequential stuff, right? Yeah. So, I mean, how to say? I'm not sure if this is like the most relevant, but I mean, we have these slides, for instance. Like again, these are actually not even in the fully paper, but like I think these are nice slides. Like but I'm not projecting. Sorry. Is there a question on the chat? Yeah. Contact info. Okay.
Use Google.
I can. Cool. Yeah. So I guess all I wanted to say is this here. Let's see if it's showing. Yeah. Regarding this, but these are hidden slides. I'm sorry. Yeah. So all I wanted to say is this, but like I have to unhide them in a weird way because like there is animation. Okay. So I just wanted to discuss this, right? Because we discussed like minimizing training risk, but we also discussed SVM geometry, right? And the feasibility. So intuitively, how large is the cone should matter, right? And how large is the cone is related to kind of interactions between the tokens, like perhaps like whether they are in the same position or not, and all those things. So the intuition is that like if there's one wide cone and the other is small cone, right? Then you might prefer the wide cone as well, even if the small cone will give you a smaller training risk, right? Again, these are without theory, but these are just intuition. So then why in the extreme, this red problem, global problem might not even be feasible. Like if the cone disappears, it's no longer feasible, then you have to go to either like some other local cone or you have to converge to a finite solution, right? So it's not feasible. So broader intuition is that basically narrow cone is related to large SVM objective. If the SVM is very difficult to solve, narrow cone, right? And that's also probably connected to generalization because flatness or sharpness, right? You know that flat solutions will generalize better. All those connections. In other words, there is more stuff going on, right? So and in the context of optimization, what we intuitively expect is that we want to achieve small training risk. In other words, we want to choose as optimal tokens as possible that minimizes the risk, while also choosing wide cone. In the extreme, if the cone is gone, I cannot choose the optimal cone. So there's a connection between how feasible is the SVM and how much I minimize the training loss, right? And they are coupled, obviously, but let's try to uncouple them. So this is what you get. If you essentially solve the problem many times, okay? And if you look at basically, if you define a margin gap, what is the margin, SVM margin of the gradient descent solution with respect to the optimal solution, global optimal solution, and risk gap, gradient descent risk minus global optimal risk. This is always positive risk gap, right? But margin gap can be whatever. So when you put all these dots on the line, right, you actually get a positive correlation. So in other words, if gradient descent picks a local solution, right, it is picking for a good reason because that local solution is most likely giving a larger SVM margin, it has a larger cone and is more feasible, right? And then potential disconnected to more generalization theory, right? So this is like Pearson correlation, blah, blah. And like one remark I have to make is that the local solution has rarely smaller margin than the global solution. Like if you go to a local solution, most likely because it's a wider one. Yeah. And you know, position encoding kind of dictates this geometry basically. Because even if the position encoding doesn't change the score of the token, it will change the geometry of the problem to perhaps prefer one direction over the other. Yeah, I guess I can stop here. I mean, I even did my hidden slides, so you know what else I can.
So how do you like think this can generalize to nonlinear, not linear solvable data? So maybe
No.
one way is like a hierarchical SVM that you can do.
Yeah, that's a good point. I mean, so I think one starting point can be either like the tokens are coming from a neural net.
Yeah,
or
so
tokens
that's,
are
I think there's a lot of empirical evidence suggesting that nonlinear network already making your features linearly separable, and then you can like interpret this as a last several layers.
yeah. I mean, there can be some connection there. Yeah, I mean because right now we are looking in more standalone. Yeah, I see basically the few options, right? You either, I mean, I guess these are the obvious things. You either assume that like tokens will pass MLP and then come at attention,
Right.
or vice versa. After attention, there's MLP. Or you somehow try to explain, okay, even in the most general setting, gradient descent is converging to somewhere, right? What is the form of the solution? Yeah. Like in other words, it went to somewhere and it selected some tokens, which is kind of the last bit I was discussing. Yeah.
Thanks.
I mean, there's not a like clear answer, but yeah, there's. Okay, thank you then.
Thank you.
Yeah, most. I mean, they didn't like. Some of them are still like